I'd like to review a little bit about the pyramid of biomass and also energy flow through the ecosystem. If you look on the left, notice the sun is the ultimate source of energy for life on the planet. And it's plants or other photosynthetic organisms that are able to take that solar energy and convert it to food, make that solar energy available to other organisms. Photosynthesis is only 1% efficient. It doesn't sound very efficient. 99% of the light hitting a plant is either reflected or lost as heat. But humans haven't been able to do anything better than that, come up with anything even closer to that in terms of converting solar energy into food. So if we look at this pyramid of biomass, notice that we have 4 trophic levels, and the trophic levels are feeding levels. And the bottom trophic level are photosynthetic organisms. Again, they're 1% efficient. But the energy level between plants and animals is 10% efficient. That means 10% of the energy available is actually converted into a bigger animal, into more animals. And so if you have 100,000 pounds of plants, you can support 10,000 pounds of ground squirrels, which could support 1,000 pounds of coyotes, which could support 100 pounds of mountain lions. Okay. And so notice that the triangle gets smaller and smaller as you go up towards the top of the pyramid of biomass. The apex predator, or the top level predator in this pyramid of biomass, is a mountain lion. And so again, this particular pyramid of biomass has 4 trophic levels. The bottom level, plants, are producers because they're capable of producing their own food. The rest of the trophic levels in this pyramid consist of consumers. And our California ground squirrel is a primary consumer. He's an herbivore and he feeds on plants. Coyotes are actually omnivores. They eat both meat and plants, but to simplify this, we'll call the coyote a carnivore that feeds on ground squirrels. He's considered a secondary consumer, and then the mountain lion would be considered a tertiary consumer. But the ground squirrel, the coyote, and the mountain lion are all consumers because they have to consume other organisms. Also, again, looking at the bottom, plants are autotrophic. Autotrophic means self-feeding. Whereas the consumers, the ground squirrel, the coyote, and the mountain lion, are heterotrophic. Hetero means other. Trophic means feeding. And so they feed on other organisms. This is a pyramid of biomass for a marine ecosystem. And notice that it has 5 trophic levels. And rather than having plants on the bottom, in an aquatic system you have phytoplankton. Phytoplankton are typically single-celled organisms that are photosynthetic. And so in our aquatic system, the phytoplankton are your autotrophs. They're your producers. And then, again, you have herbivores that are feeding on the phytoplankton. And in this pyramid, we have small carnivores, which would be secondary consumers feeding on the herbivores. And then we have large carnivores, which would be tertiary consumers feeding on the smaller carnivores. And in this system, our apex predators, our top-level carnivores, would be tuna, swordfish, and sharks. And notice that at each level, again, the efficiency is 10%, which means 99% of what is eaten is either lost as heat or waste from the animal. And then again, notice that we have 5 trophic levels in this pyramid of biomass for a marine ecosystem. And then that takes us to a term that I want you to know, and that term is primary production. And an easy way to define primary production is it's a measure of the rate of photosynthesis. The sun is the ultimate source of energy for life on the planet, and the amount of photosynthesis that takes place in an ecosystem is going to determine how much energy is actually captured and funneled through that ecosystem. Because deserts are limited by the amount of rainfall, and the amount of rainfall is going to limit the amount of photosynthesis, deserts, on average, produce about 200 pounds of edible vegetation per acre per year, which means in a desert, 1 acre of desert would support about 20 pounds of herbivores and about 2 pounds of carnivores. And so you don't expect to find lions and tigers and bears in a desert. Your carnivores are typically snakes and lizards, because again, 200 pounds of edible vegetation will only support 20 pounds of herbivores, which will only support 2 pounds of carnivores. In a tropical rainforest where you have 10,000 pounds of edible vegetation produced per acre per year, you have lots of photosynthesis, and you can support much larger animals on an acre of tropical rainforest than you can in an acre of desert. And so some examples of producers or autotrophs, organisms capable of photosynthesis. On the right, you see a picture of a Douglas fir in an old-growth forest. And on the left, you see a microscopic view of a diatom, which is a component of marine phytoplankton. Primary consumers are herbivores. This happens to be a Roosevelt elk in Prairie Creek State Park. And all consumers are heterotrophs. They feed on other organisms. And then secondary consumers feed on primary consumers. In this case, the mountain lion is a carnivore that could feed on a Roosevelt elk. And so if we had a simple 3 trophic level pyramid of biomass, you would have the Douglas fir and the vegetation of the forest supporting the Roosevelt elk, and your apex predator being the mountain lion. And then, as I mentioned in the very first slide, coyotes actually act as both primary and secondary consumers because they will eat small rodents, they'll eat rabbits, they'll eat ground squirrels, but they'll also eat cactus fruit and other types of vegetation. And an animal that eats both plants and animals is referred to as an omnivore. Decomposition is another important component of this whole system. This happens to be a log on a beach in Costa Rica where there's a bunch of fungus helping to decompose that log. Bacteria and fungi are major organisms of decomposition, and that's very important in recycling nutrients through the system. You're going to be seeing a movie on the Serengeti, and so I want to show you a pyramid of biomass for an African savanna. This one is a little unique because it takes you a level below your producers and shows you the importance of nutrients to the growth of plants. Notice that there's phosphorus and nitrogen in there. Notice water is also important to the growth of plants. And then on the bottom, on the right-hand side, it shows termites, which in the African savanna are very important in terms of recycling nutrients. And so in your classic pyramid of biomass, we'd start with the plants of the savanna, okay? And the plants, again, would be our producers, our autotrophs, which would be fed on by primary consumers, which would be your herbivores, which would be the antelope and the wildebeest in the picture. And then your secondary consumer would be the lion. And then your apex predator in this situation would be a human. The movie is going to be talking about top-down and bottom-up regulation of populations, and specifically it's talking about wildebeest populations. And so in this pyramid of biomass, we have 3 trophic levels. The wildebeest are herbivores, they're our primary consumers, and then the predators are our secondary consumers. And wildebeest can be regulated by predators, where predators determine the number of herbivores. That's referred to as top-down regulation. Some examples of top-down regulation. You see these cheetahs on the right coming over the hill. They're hunting these Thompson's gazelles. And typically small ungulates are regulated by predators, and so that would be top-down population regulation. This lion is also feeding on a small ungulate and an impala. And again, small ungulates are regulated by top-down regulation. The predator determines the herbivore numbers. Bottom-up regulation is when the amount of food available is going to determine how many herbivores you have in your ecosystem. And some examples of bottom-up regulation are what are referred to as the large herbivores in the African savanna, or the mega herbivores. On the top left, you see a hippo. The hippo is considered a mega herbivore, and hippos are basically regulated by the amount of food available, so that's bottom-up regulation. A young giraffe is vulnerable to predators, but a full-grown giraffe is not very vulnerable to predators. So again, that's bottom-up regulation. The same thing with elephants, and the same things with rhinos, which is the bottom left picture. This is a picture of wildebeest crossing the Mara River, and again, that film you will watch on the Serengeti, it turns up that the wildebeest that migrate. There's two populations of wildebeest in East Africa. The majority of them migrate, and so they are regulated by bottom-up regulation. But there are some populations that don't migrate that are regulated from the top down. But you'll see more of that in that movie. The last thing I want to mention is the impact that a change in an environment can have on energy flow through the system. Okay. One of the things that biologists are finding in the Arctic is that seabird populations are declining. And in this particular picture, you have a picture of an Atlantic puffin. And their populations are declining dramatically, and people are beginning to figure out what is happening. Why are these seabird populations declining? And so if we look at a typical Arctic Ocean pyramid of biomass, again, you have the sun as the ultimate source of energy. And that solar energy is converted to food by phytoplankton. And in cold waters, that's typically diatoms. And in the Arctic, it turns out that the sea ice is extremely important because much of the phytoplankton grows on the underside of the sea ice. And the sea ice is kind of analogous to the soil of the garden. And it's very important in order to have large populations of these photosynthetic organisms. In the classic food chain in the Arctic, historically, herbivorous zooplankton feed on the diatoms or the phytoplankton, and the particular species is a species of copepod that hibernates, and it's able to because it hibernates, it concentrates a fat called omega-3, or actually it concentrates fats that contain omega-3 fatty acids. And it also concentrates proteins. And so this is what I'm going to refer to as a high-fat copepod. It's a hibernating copepod that is a source of fat and protein for animals that feed on it. And so our herbivorous zooplankton, or our high-fat copepod, would be our primary consumer. Our secondary consumer would be a small fish called a sand eel. So these sand eels are feeding on these high-fat copepods once the ice starts to melt. And then puffins are feeding sand eels to their chicks. Well, with climate change and increasing ocean temperatures in the Arctic, what's happening is you're getting a change in species composition of your primary consumers. Historically, we had that high-fat copepod, but if you look at the graph from 1960 to 2000, the population density of our high-fat copepods has decreased dramatically, and they've been replaced by a low-fat copepod, which has increased dramatically between 1960 and the year 2000. And so in the Arctic Ocean, due to warming temperatures, we're losing our high-fat copepod, and we're replacing that with a low-fat copepod. And that's had a dramatic impact on seabird populations. Because when our low-fat copepod is fed on by sand eels, they don't gain the weight that is needed to provide enough energy for those chicks to grow up and fledge. And so with warmer seas, we've got low-fat copepods, we've got thinner sand eels, and we have mackerel, which is a fish that prefers warmer water, moving in and competing with the seabirds for these skinny sand eels. And so you end up having hungry seabirds and dead chicks. And this is not only impacting puffin populations, but it's also impacting other seabird populations in the Arctic. And so what we have is a trophic cascade where we're getting a collapse of the system because warmer seas are leading to a lower fat copepod, which is resulting in skinny or absent sand eels, being absent because you have mackerel moving in and feeding on them. And so you have hungry seabirds, you have dead chicks, and you have collapsing seabird populations.